Last time we considered torsion of segmented box sections. Today we would like to illustrate the formula that we have derived by considering one example. The problem is shown here. The segmented section is illustrated. We have one cell formed by A, B, C, D, another cell formed by A, D, E, and the thickness of the wall A to B, then B to C and C to D. So, also from D to A there is same thickness, it is 0.9 millimeter, and the portion DEA is of thickness 0.6 millimeter. The length of the portion AB is 670 millimeter, BC is 480 millimeter, CD is 630 millimeter, AD is 330 millimeter, and this length DEA is 670 millimeter. It is given that the torque of magnitude 10 to the power 7 Newton millimeter is applied. The areas enclosed by the cell 1, that is A1, is 68 into 10 to the power 3 millimeter square. So, also the cell 2, its area is 200 into 10 to the power 3 millimeter square. What is required is that find out the flows in the cell 1 and 2. So, that means you have to find out Q1 which is in this loop and Q2 in this loop. So, note that this Q1 is flowing in the same sense as the applied torque, Q2 is also acting in the same sense as the applied torque, and the net flow in this segment A to D is Q3, it is directed in this direction. So, that is the direction of the flow Q3. So, we will look for the solution. First, let us consider the point D. For the point D, flow leaving the point is Q1, flow coming in towards the point is Q2 and Q3. So, from the flow equality, we can write Q3 is equal to Q1 minus Q2. So, this is how the flows are related, and this also can be obtained from the consideration of equilibrium. Now, let us consider the cells DEAD. Now, let us consider the cell DEAD and ABCDA. So, these two cells separately, and if we consider these cells separately, then for the first cell we will obtain the torque taken by the first cell, cell 1, is going to be given by the formula, that is the Bredt-Bethe formula directly. T1 is equal to 2 Q1 into A1, where A1 is the area enclosed by the cell DAD. Similarly, torque taken by the second cell ABCDA is T2 is given by 2 times Q2 into A2, wherein Q2 is the flow in the cell and A2 is the area enclosed by the cell. So, adding the two equations or two relations, we get the total torque, which is T1 plus T2, and therefore, this is 2 Q1 A1 plus 2 Q2 A2. Now, if we substitute the values given, this is 10 to the power 7 and A1 is 68 into 10 to the power 3, A2 is 200 into 10 to the power 3. So, we get this equation. Finally, we can make some simplification and we get the relationship 136 Q1 plus 400 Q2 equal to 10 to the power 4. Let us consider that equation number 2, and already we have got equation number 1, which is Q3 is equal to Q1 minus Q2. Now, if we consider again the two loops separately, so we will consider the loop DEAD, then we can write 2 g theta into A1 is equal to integration of the product tau into ds over the whole loop, and since length of the portion DEA, or rather thickness of the portion DEA is constant, we can write this tau in terms of length of DEA, flow over that portion is Q1 divided by thickness of DEA. Similarly, the portion AD, its length is LAD and Q3 is constant, therefore, Q3 by TAD, it gives us the shear stress which is constant. Now, we can substitute the value of the areas and also the thicknesses, then we get this relationship. On simplification, this turns out to be 16.42 Q1 plus 5.39 Q3 is equal to 2 into 10 to the power 3 G3 G theta, I am sorry, 2 into 10 to the power 3 G theta, that is equation number 3. So, we get another relationship involving the two flows and the angle of twist per unit length theta. Let us consider application of similar relationship for the second loop, which is nothing but A, B, C, D, A, and we can write now 2 g theta into A2 is equal to over the whole loop A, B, C, D, A tau into ds, and since the thickness over the portion A, B, C, D is constant, we can replace this thing by Q by the thickness of the portion TAB and length of the portion ABCD. Similarly, for this portion DA, we are, this is something you can note, that when we are trying to talk about this loop, we are trying to move in this direction, and since Q3 is in the opposite direction, shear flow is directed in the opposite direction of the path, therefore, we have to take negative sign. So, LDA minus Q3 divided by TDA, that is the value of the integral from D to A. So, we have constant thickness all over this, therefore, we could write straightaway length ABCD into Q2 by T of AB, and for the remaining portion you have to write this negative sign comes up because the movement is in this anti-clockwise direction, but the flow is taking place in the clockwise direction. So, if we substitute the value of the areas and the thicknesses, also the lengths, then we get this relationship 9.8889 Q2 minus 1.8333 Q3 is equal to 2 into 10 to the power 3 g theta. So, that is equation number 4. So, we have 4 equations. The first equation is Q3 equal to Q1 minus Q2. Second equation gives us 136 Q1 plus 400 Q2 is equal to 10 to the power 4, and then we have got third equation which relates Q1 and Q3 to g theta, and the fourth equation it relates Q2 and Q3 to g theta. Now, in the problem we have unknowns. What are the unknowns we have? We have 4 unknowns. They are nothing but Q1, Q2 and Q3, and at the same time angle of twist theta, and we have 4 equations. We have sufficient number of equations to solve for the number of unknowns. Once you solve it, you obtain g theta as 0.10448 and Q1 equal to this, which is equivalent to 14.5 Newton per millimeter. Q2 is 0.192 into 10 to the power 3 g theta, which is nothing but 20.06 Newton per millimeter, and also you can obtain Q3, which is 5.56 Newton per millimeter. So, this is how you can solve the problems involving segmented box sections. The process can be repeated even if you have more number of closed loops. The application can be done in a routine manner. Now, to get some physical feel about the box sections, rather how the stresses develop in the box sections, I would like to get back to consideration of membrane analogy for thin box sections. What I am concerned really is the following sections. You have a section of this type, or you have a section of the triangular shape, or you could have a section of this type. They are all subjected to angle of twist. Now, if the membrane analogy is to be considered for such sections, how do you go about it? We have given you the membrane analogy for solid rectangular sections, square sections, triangular sections, elliptical sections, but if we have thin box sections, how do we consider the membrane analogy? Just to get back to membrane analogy, if you recollect that if we have to have a membrane analogy for this type of section, then in that case the sealed box was like this, and we had a opening here. That opening should correspond to the outer boundary of the section. So, in this case our outer boundary is like this. So, we have the outer boundary. Now, in this case, since the section is not solid, since it is hollow, we consider a metallic plate sort of placed like this. Now, a membrane is tied between the outer boundary and this metallic plate with constant uniform tension per boundary. What I mean is that we try to tie the membrane at the outer boundary and also to the boundary of this metallic plate, and there is tension per unit length of this boundary which is constant. Now, if you try to apply the pressure, so the box is now closed by the wall of the box and the membrane and this metallic plate. If we now increase the pressure, the membrane is going to deflect like this. So, if we carefully look into it to a larger scale, so this is the outer boundary and the metallic plate is located there, and the membrane has now deformed like this. So, this is the central plate. You remember that the membrane, the function Prandtl's stress function phi is proportional to the deflection of the membrane, and since phi is to be 0 here, 0 at the outer boundary. So, we have 0 deflection all along the boundary, and this phi is constant along the boundary. It also due to the fact that there cannot be any shear stress acting perpendicular to this boundary. So, this phi is constant along the boundary, because if there is going to be a stress acting perpendicular to this boundary, then the slope along this boundary cannot be 0. But since phi is constant along these boundaries, the slope is 0 in this direction, therefore, shear stress in this direction is equal to 0. By the same reasoning, there cannot be shear stress perpendicular to this boundary, because the surface, inner surface of the component is not subjected to any stresses, and therefore, there cannot be any shear stress perpendicular to this boundary. And if this shear stress cannot be present perpendicular to this boundary, the membrane deflection has got to be constant along this boundary. So, therefore, all along this boundary, internal boundary also, the membrane deflection has got to be constant. So, while this membrane is deflecting, we must ensure that the deflection of the central plate is constant. So, there is a constant elevation of this central portion, and hence all along the boundary of the membrane we have the deflection constant, hence Prandtl's membrane Prandtl's stress function is also constant. So, I repeat, to ensure the shear stress to be 0 perpendicular to this boundary, the membrane deflection has got to be constant, and therefore, we must ensure that the central portion is going to have constant deflection in the vertical direction. You can imagine the situation that, think of a case that you have the soap bubble attached to this outer cutout, and then you apply the pressure, it will inflate, then you try to bring in one plate like component to truncate the membrane or that soap film, and that is what is the type of situation we are trying to talk about roughly. It is not exactly so, but it is roughly like that. So, you can understand now that this is the membrane, which is, if you try to take a section along the vertical plane here, this is the membrane, and therefore, the shear stress is going to be constant. You see that slope, you can approximate this thing by a straight line, and the shear stress is approximately constant, and you find the shear stress to be parallel to the boundary, and it is of constant intensity, or shear flow is constant along this direction. Similarly, if you consider this direction, you will also find that this intersection of the membrane with the vertical plane passing through this straight line will also have, you will observe the deflection of the membrane to be like this, that you have this and then this is the central plate, and then of course we have the deflection here. So, therefore, this is the central plate and this is the deflection of the membrane, and this is the wall of the box. So, this is the membrane. Here also you can see that the slope is more or less constant, and therefore, shear flow will remain constant along this segment. Thus, if the thickness of the wall is constant, you are going to have constant shear stresses coming up at each point of the boundary, and it is going to be directed parallel to the boundary. If the section is of this type, then your outer cutout in the box will be like this, and the central plate will have a shape conforming to the internal boundary of the triangular box section, and you make sure that the membrane is attached to the outer and inner boundary with a constant tension per unit length, and then try to deflect the membrane, making sure that the central portion has a constant deflection, then you will get the shape of the membrane. So, this is how the membrane analogy can be applied to thin box sections. Now, after considering closed sections, let us look into thin open sections. What do you mean by this? You have sections like this, very slender rectangular sections like this, or you can have sections of the L shape, or a T section, or a circular section, but it is not closed. So, these are examples of open sections. I would like you to consider the membrane analogy for these sections. Think of the rectangular section. Let us consider that its height is B and its thickness is equal to T. The torque applied is equal to T. If we consider a membrane to be attached, then the membrane deflection will occur. If you look from this direction, or if you consider the intersection of the vertical plane passing through the center, let us introduce the axis as x and y. So, these are the axes. If we consider a vertical section containing the x axis, the intersection of the vertical plane with the membrane will give us a curve like this. So, this is the membrane shape. Similarly, if we take a vertical plane passing through the y axis, then the intersection of that plane will be somewhat like this. So, this is the membrane. So, this is the shape of the membrane that you are going to get, and here it is this. It is also very clear that these shear flows or shear stresses will be directed like this, along this boundary it will be directed like this, along this boundary it will be directed like this. Similarly, along this boundary it is going to be directed like this. So, it takes place in a current in the same sense as the applied torque. If we see, if you forget about this portion here and portion there, since the deflection of the membrane in the central region is constant, we can expect to get the same shape from this portion to somewhere this portion. So, approximately if we neglect the two edges, the membrane shape is going to be constant and it is independent of the coordinate y. So, let us draw this to a larger scale. So, we have these shear stresses directed like this, looking into the membrane shape. What I was saying, that the shape of the membrane over the portion from here somewhere there, if you look from this direction it is going to look the same. If we look into the equation, governing equation of the torsion, it was in this form: delta 2 phi delta x square plus delta 2 phi delta y square is equal to minus 2 g theta, wherein we had already considered that tau xz is nothing but delta phi delta y and tau yz is equal to minus delta phi delta x. If we just neglect the portion of the membrane around the top and bottom edges, what we find is that this membrane shape is independent of y. So, phi, which is proportional to the membrane deflection, and this is independent of y. So, from this equation number 1, what we get is that delta 2 phi delta x square is equal to minus 2 g theta, that is phi is just a function of x. So, we can now write phi is equal to minus g theta x square plus some constant a1x plus another constant a2, that is the form of phi. How do we get the two constants a1 and a2? We have the boundary conditions that phi is equal to 0 at this boundary, which is x is equal to minus t by 2, and it is also 0 at this boundary x is equal to plus t by 2. So, therefore, what I am saying phi is equal to 0 here. So, also it is 0 at this boundary. So, we can introduce these conditions. Boundary conditions are phi equal to 0 at x is equal to plus minus t by 2. So, if we substitute the values, what we have, g theta t square by 4 minus a 1 t by 2 plus a 2 is equal to 0. Similarly, for x is equal to plus t by 2 plus a 1 t by 2 plus a 2 is equal to 0. So, we have two equations to solve for the constants, two constants, and once you solve for it, you find that a 2 is equal to minus g theta t square by 4 and a 1 is equal to 0. Substituting the values for the constants, what we find finally is that phi is equal to g theta into t square by 4 minus x square. So, that is the variation of phi with x. We also know that the torque capacity of the shaft is given by 2 times the integration of phi over the whole area. So, if we consider that relationship, we have T equal to 2 times integration of phi over the area, and this therefore means that we have to do the integration from minus t by 2 to plus t by 2 g theta t square by 4 minus x square dx, and integration of y is minus b by 2 to plus b by 2 dy. Once you do this, we get this simplified to the form g theta b t cube by 3, that is t equal to g theta b t cube by 3. Now, if we calculate the stress, so let us now calculate the stress at this point at the intersection of x axis with the right boundary. So, that stress is nothing but tau yz, and it is going to be maximum stress. So, tau yz x is nothing but delta phi delta x at the point y equal to 0, x is equal to t by 2. So, this gives us since our form of phi is already known. So, if we do that, it is g theta minus 2x. So, minus 2x become plus, and it is y equal to 0, x is equal to t by 2. So, if we do that, it gives us g theta into t. So, the maximum shear stress is this much, and since we have g theta available in terms of torque, if we substitute value of g theta equal to 3t times b2 cube, then it gives us 3t by bt square. So, that is the maximum stress. So, this is how you find that the problem of thin rectangular sections can be tackled. The angle of twist per unit length is related to the applied torque by the relationship T equal to g theta bt cube by 3, and the maximum shear stress which acts at the boundary is going to be 3t by bt square. So, we have seen the rectangular section, that it is more or less the stress is constant along the longer at the edge of the longer boundary, and it is given by g theta into t, and at the same time the torque capacity is given by g theta into bt cube by 3. The same analysis can be applied to sections of this type, or here, or even this. If T is acting in a cross section like this, then the flows are going to be directed, this part of the boundary it will be like this, here at the bottom edge it will be directed in this manner, at the top edge it will be directed here, and on this edge it will be directed like this, and this will close the flow and it will got to be directed like this. Similarly, here also it is going to be directed like this. You can also consider similar picture here, that the flows are going to be directed at the edges like this. For this section, if this is the torque, then at the outer boundary it will be all anti-clockwise, and at the inner boundary it is going to be clockwise. And of course, at the edges it will try to close the loop. So, therefore, here it will be like this, and at this edge it will be like this. Neglecting this junction, the shape of the membrane over this portion we can consider to be same as the shape of the membrane here. Similarly, the shape of the membrane over this segment can be compared with the shape of the membrane here. And since the stress is going to remain constant at the edges, we can write the stresses in terms of the angle of twist per unit length and the thickness here. For this segment also we can write the stresses in terms of the angle of twist per unit length and the thickness here. And the torque capacity for this portion can be written in terms of angle of twist per unit length and the length of this segment and the thickness. For this portion also we can write in a similar fashion. Similarly, here we can just consider this to be consisted of two portions. We can consider it to be consisted of this segment, rectangular segment, and this rectangular segment, and we can apply the membrane analogy. And in this case you can just develop it, and you are going to have a strip of length approximately equal to the circumferential length, and it is a rectangular section like, and hence we can find out the capacity of this open section from the results that we have obtained there. So, we would like to illustrate this with examples. So, let us consider the examples. First, let us consider this example 1 on this type of section. So, here we have this portion of length equal to B1, this is thickness T1, and let us say that the remaining portion is B2 in height and T2 is the thickness. If you try to consider the axis to be oriented for this segment 1, let us say that x1 is in the thickness direction, y1 is in the height direction, then for this branch, for B1 T1, we can write phi as g theta T1 square by 4 minus x1 square. Similarly, for branch 2, B2 T2, we can write phi is equal to g theta T2 square by 4 minus x2 square, provided you consider that the axis for this segment is like this. Now, if I apply the formula for torsion for the portion B1 T1, torque T1 is going to be equal to g theta B1 T1 cube by 3. Similarly, for the portion 2, T2 is going to be g theta B2 T2 cube by 3, and hence the total torque is equal to, given by the sum of the two torques T1 and T2, and that must be equal to g theta into B1 T1 cube by 3 plus B2 T2 cube by 3. So, that is the total torque. Now, in this case, what is asked for is calculate the theta and maximum shear stress for the given torque T. So, we have got the relationship here relating the angle of twist per unit length with torque, and therefore, your theta is given by T by g B1 T1 cube plus B2 T2 cube by 3. You can now calculate the maximum shear stress. Maximum shear stress for the branch 1 is going to occur here, and it will be simply g theta into T1, and for the branch 2 it is going to be here, which is nothing but g theta into T2. So, therefore, for branch B1 T1, maximum shear stress, maximum tau. So, if we write maximum tau in branch B1 T1, it is nothing but g theta into T1. Similarly, maximum tau in branch B2 T2, it is given by g theta into T2. So, we have got both the angle of twist per unit length and also the value of stresses in both the segments, and obviously, if T2 is larger than T1, you are going to have larger stresses in branch number 2. Let us consider another example. Let us now consider example number 2. Herein what we have two sections. One is closed box sections of uniform thickness, it is circular in shape, and another open section the radius in both the cases are same. So, let us consider this case A and case B. So, we have thin circular sections here, and in the other case we have open circular section. So, what is needed is that compare the stiffnesses of the two sections and also compare the maximum stresses. So, we will try to solve this case. First of all, if we consider the closed section, we can apply the formula that we have derived in the strength of materials course related to circular cross section. So, we can write for the section A, tau by r is equal to g into theta, where theta is the angle of twist per unit length, and therefore, for this case tau is equal to g theta into r, and let us say that this is the shear stress maximum in the section A or problem A. Now, TA, since it is a thin section, we can consider the shear stress to be uniform all along the thickness, and therefore, shear flow is constant, and shear flow is tau A into T, and that is the force per unit length of the boundary. And if we consider the whole boundary, which is 2 pi r, the total shear force is nothing but 2 pi r into tau A into T, and if we take the moment of those forces about the center, we have to multiply by r, and therefore, this moment that we get is nothing but tau A into T, that is the shear flow multiplied by the total circumferential length, that gives us total shear force, and it is acting at a distance of r. So, therefore, that is the total moment, and therefore, this is 2 pi g theta r cube into T. That is the torque in the case number 1. Now, let us go for the case number 2. For case number 2, we can calculate now TB. Now, we make use of the formula that we have derived for the rectangular section, that g theta b t cube by 3. So, herein b is nothing but length of the whole circumference, which is nothing but 2 pi r. So, we can write now g theta multiplied by L is the total length of the circumference. So, that is the total length of the circumference, L T cube by 3. It is simple application of the formula that we have derived for the thin rectangular sections, and that gives us 2 pi g theta r T cube by 3. What is stiffness? Stiffness is defined as torque per unit angle of twist. So, we can now write Ka, stiffness of the section A, is given by Ta by theta. Similarly, Kb is the stiffness in the case 2, it is given by Tb by theta. So, that is the second case. So, if we now try to take the ratio of the two, we will get this, and since we know the value of T by Ta by theta, Tb by theta, if we substitute, that gives us 2 pi g theta r cube into T by 2 pi g theta r T cube by 3. This gives us, on simplification, 3 times r by T square. let us get the numbers. If r by t is equal to 5, then the stiffness ratio Ka by Kb is equal to 75, and if this ratio is 10, then this ratio is going to be 300. So, look at this, just to, if we make the section open, the stiffness changes substantially. The stiffness of the closed section is much higher compared to the thickness of the open section. The second part, we have to calculate the shear stresses in the two cases. Now, if I consider the case 1, tau in case A maximum is equal to g theta into r, and tau in the case B, and the maximum value is equal to g theta into t. So, you can look into the magnitude, order of magnitude of the stresses. If r is larger than t, you are going to get larger stresses developed in the closed section compared to that in the hollow open section. So, the higher stresses are going to develop, and also you have seen that the stiffness in this closed section is going to be much higher. So, the capability of the angle of twist, or rather actually torque capability in the case of closed section is much higher, and also the stresses developed are going to be much higher. So, with this we have illustrated how the thin sections can be dealt with very easily. You can consider problems for solving to get clarity on the theory that you have dealt with in the torsion of non-circular sections. You can look into the problems which are not solved in the Advanced Mechanics of Solids by L.S. Srinath, second edition, which is published in 2003 by Tata McGraw-Hill.